Alright, in this video, we will go over the coefficient of determination, also known as the R squared. So when it comes to types of analysis for the regression equation, more so for the beta squared, there are three main types of analysis. So the casual analysis of beta squared is kind of like what we've done before. So, calculating the slope, elasticity, and then kind of just how much of that impacts y. Obviously, we've done it for different functional forms, so the slope isn't always beta squared, neither is the elasticity always beta squared times x over y, but that's what we just calculating the slope and elasticity for different types of functions for the regression. It's what we call the casual analysis. The prediction is similar. I didn't cover over how we can mathematically predict, but it's pretty similar to kind of just a regression function. When we're analyzing the regression function, we're kind of looking into the past, but when it comes to predicting, we'll utilize the past values to make a prediction for the future, which is also known as kind of like forecasting. But a lot of the variables for prediction also take into factor of cross validation or machine learning, or and like future different calculations of standard errors. So I didn't cover mathematically how to go over that, but that is another type of casual analysis we do for the regression equation. And then finally, what I'm going to go over today is the coefficient of determination, or the R squared. And basically what that does is it measures how much variation at y in the dependent variable is explained by the independent variable. So how much of x actually describes y, or how much effect there is. Note how that's different from the casual analysis, because all the casual analysis is saying is what the slope is. Elasticity, I guess, is a little similar, but casual analysis, we're kind of looking at the just the raw impact of y in relation to the beta squared, and the R squared is saying how good is x at describing y, like how much overall how much does it have an overall impact, or like what proportion of y is explained by x, I guess. So in the equation, if we include every part of the equation, so beta 1 plus beta 2, if we exclude the error, that's what we will call the explainable part of the equation, and then the error is the unexplainable. So looking at this equation here, we the very right part of the equation, the error squared, that's what we already covered, which is the sum of squared error. So taking the residuals and then squaring it and then summing it up, the SSE, what I noted down here. And then, but what you'll notice is to the left side of the equation looks a bit less familiar, because we're taking the fitted values of y, so our like predictive values, not our actual, but our predictive values of y, and then subtracting that from the mean. Because what we're doing from the R squared is we're basing it off, we're determining the coefficient of determination, or the R squared, based off the mean. So if we subtract the fitted values from the mean and then square it, that's what we'll call the sum of squared regression, short for also known as SSR. And then if we add those two up, that's what we'll get the SST, the sum of squares total. And then notice here how we're adding the difference of the actual y values from the mean. This can get a little tricky at first, but I think it's more important to understand conceptually. I still think the most right part of the equation, the sum of squared errors, is what we should focus on the most. But for the sake of knowing how we actually get the coefficient of determination, I think this isn't necessary. And so if we divide all the variables in the equation by n, we'll call the SST over n the outcome variance, which is the explained variance plus the unexplained variance. Again, the SSE we call the unobserved or an unexplainable part of our data. Okay, so the reason why I showed all that is because r squared is equal to the explained variance over the outcome, or the sum of SSR over SST. This is when we divide by n, so this isn't exactly correct, but SSR over SST, sum of squared regression over sum of squared total, equals 1 minus sum of squared error over sum of squared total. As if we look at this equation, then this part also makes sense. And so we can create trends for that, saying if the sum of squared regression increases, then obviously the r squared will also increase. And if the errors decrease, or the errors increase, I guess, then the r squared decreases, which would make sense because the higher our errors, the higher our errors, or the worse our fitted equation is, then the r squared, which we defined as how good x is describing y, would be lower because we have more errors into our fitted equation. All right, so some of the properties of the coefficient of determination is that if it's very close to 1, similar to correlation, or I guess not correlation, but r squared is defined as a proportion, like similar to a probability, I guess. It will always be from 0 to 1, and if it's close to 1, that means x is very good at describing y, and if it's closer to 0, that means there's very little linear association. Kind of like correlation, except correlation can become negative, r squared can't. And then from the properties of correlation, this is a little confusing, but if we kind of analyze more of what we did here, then we'll realize that the r squared equals the correlation of x and y squared, not beta 2 or beta 1, but x and y. As well as it also equals the correlation of our fitted y and the actual y. I don't have any proofs for this. I think the proof would stem somewhere down from here, or just the mathematical definitions of correlation and the fitted values, the residuals, and all that. But this is what I have for my notes, and I can almost ensure that this is correct. Same for the bottom equations here. So what we're doing is we're standardizing our explanatory variable. So if we want a more proportional slope for our beta 2, then we can standardize our x and y by dividing by the standard error of it. And then our beta 2, standardized beta 2 that is fitted, we can write into this equation. Not going to overanalyze what we've done here, but simply when we do all this, we get a correlation of x and y. So now we've translated the beta 2 tilde hat into just the straight up correlation of x and y, where it's scaled from -1 to 1. And so therefore the beta 2 will give us the impact on y scaled from, this is actually incorrect. Let me rewrite this again. Give us the impact on y scaled from -1 to 1. Okay, so again, usually we would just use a raw slope of the beta 2, but when we're given less of information of how beta 2 acts in relation to y, then I think these properties of equations useful. Okay, that is it for the r squared, or the coefficient of determination. In the next video, I'll go over linear and nonlinear transformation.